마이크. Is it okay? My voice. 하나, 둘, 셋.
This is. I'm gonna stick it up here.
Uh-huh.
There you go. That's better.
Okay. Is it good? Mm-hmm. So until 30, right? Or
Next, we have Donggyu Kim, who is actually from IBS, talking about Baker-Bowler theory for Lagrangian Grassmannians.
yeah. Thank you for the introduction. Yeah. So here, Bowler is Nathan Bowler, so who is here. So I'm very appreciative to talking about some extension of his theory. So okay, let me introduce what is the Baker-Bowler theory and the Lagrangian symplectic Grassmannian is first. So actually, the Baker-Bowler theory is one fascinating result about the Matroid with coefficient, which is unifying many different concepts like oriented Matroid or just ordinary Matroid or evaluated Matroid and so on. So I did not define the track yet, but it's something like field-like object, which of course extending the field, also partial field or the hyperfield. So if we're taking just F as a field, then this is nothing but a usual vector space. And if we take a partial field, this is quite related with the partial field representation. And if we consider F as just some hyperfield which only consists of the zero and non-zero elements, then this is just ordinary Matroid. It's just Matroid. And if we take some sign hyperfield, then this is oriented Matroid. And if we take some tropical hyperfield, so this gives also the evaluated Matroid. So it's combined, it's unifying many different concepts. And okay, let's move on to the second one. So the Grassmannian is nothing but, as you know, that the space of the full-length D by N matrix, or maybe you can understand also the D-dimensional vector space lying in the ambient N-dimensional vector space. And Lagrangian symplectic Grassmannian is nothing, you can roughly understanding this as the space of the N by N symmetric matrices. So goal of this talk is give you some Matroid-like object which extending some Matroid with coefficient concept. So one remark is that actually Dongjin and I already extend this theory for the space of the skew symmetric matrices in terms of the even delta Matroid. So you may wonder that, for the symmetric matrix, you may consider the delta Matroid. However, there is one short point of the delta Matroid. What it is it does not have the strong basis exchange action, which is very crucial in this theory. So okay, let's go back to the definition of the Matroid first. So as you know that we can define Matroid in terms of the basis exchange axiom. And yeah, if you consider some linear Matroid consisting of the columns of this matrix, and if we take some basis B1 and B2 like this, and if we take element E, then we can find another element F, another column F, such that this is a basis. However, you can easily observe that this is not a basis. However, if you take our F very carefully, then you can guarantee that both exchange output the basis simultaneously. And this is the reason why this is quite related with the flicker embedding. So if you have some D by N matrix, full-length D by N matrix, if you can embed this into the projective space using the maximal minors. And what we also know is if we consider the point in this projective space, which is the image of some vector space, then you can easily check that this is satisfying the certain quadratic relation. So okay, also you can understand this as a Laplace expansion of the usual matrix determinants. And because of that, you can easily check that actually the linear matrix satisfying the strong basis exchange axiom. And we already know that this is generally true for any Matroid. Yeah. Also, yeah, we can rephrase this as this language by, this is more compatible with the Grassmann-Flicker relations. Okay, so let's move on to the other one. So I will introduce roughly I already introduced what is hyperfield, partial field, and tracks. So hyperfield is something like field-like object such that addition may output the more than one element. For example, this is the Krasner hyperfield, which is the terminal object of the track. So the multiplication table is same as before, but the addition table is a little different. So if you sum if you consider the 1 plus 1, then it may output the 0 or 1. So you can consider 0 as a 0, but 1 is some symbol representing the all non-zero elements in the real field or any other field. So you can consider if you sum up two non-zero elements, then it may give you just 0 or non-zero. So if you and then in this concept, Matroid is nothing but a Flickr vector over the Krasner hyperfield, and which you already observed in this slide. And yeah, strong basis exchange axiom is just nothing but a Flickr relation over this Krasner hyperfield. And if you consider something else like sign hyperfield, so here plus represent for the all positive numbers in the real field, and negative is something the other way around. Then if you consider the summation of the positive numbers and the negative number, then it maybe it give you some positive number or 0 or negative. So yeah, this is the concept of the sign hyperfield. And if you consider about the Flickr vector over the sign hyperfield, then this is nothing but an oriented Matroid in the sense of the Kirotov axiom. And yeah, also let's move to the other way around. So if you consider the partial fields, I think some of people who are working on the matrix representation of the Matroid are familiar with this concept, of course. So for the partial field, it is a little different. So when you sum up two elements, then it may output nothing. What I mean is the summation of the 1 and 1, plus and plus, is do not define. In the real field, it is 2, but we just ignore this. And same for the -1 plus -1. So if you consider the Flickr vector over this regular partial field, is nothing but exactly the totally unimodular matrix. So Baker-Borlo theory offers some unified theory for these concepts. And yeah, Lagrangian symplectic. Yeah, so let's move on to something else. So Lagrangian Grassmannian is, I already said to you that this is kind of space of the symmetric matrices. And here is some terminology. What I will use is our ground set is something 1 to n, and with 2n elements with this linear order. And I will say a pair of the element is skew pair. It looks like this, and transversal and almost transversal is just nothing but an element subset which contains no skew pair or exactly one skew pair. And then Lagrangian Grassmannian is the original definition is the set of the maximal isotropic space with respect to the symplectic bilinear form, but you can easily convert this into the n by n symmetric matrices. And luckily, we also have some kind of embedding of the set of the n by n symmetric matrices into the projective space. So how you can do that is very similar to the Flickr embedding. Here is a sigma, is our n by n symmetric matrix, and we are attaching it together with the identity matrix. Then we have the n by 2n matrix, and consider about the all maximal minors with the certain condition that here x and y must be same or differ by only one element. Then using this kind of information, you can parameterize this into the projective space, luckily. And what I check is actually this can be theoretically cut out by the certain, very simple Grassmann-Flickr relation with the condition on S and T would be those like this. Maybe you can just neglect, sorry. Yep. So here, S must be the n plus 1 element subset which contains exactly one skew pair, and T contains no skew pair. And then S minus E must be either transversal or almost transversal. And also same for the T plus E. It must be the transversal or the almost transversal. then I just introduced the anti-symmetric matroid which contains which corresponding to the symmetric matrix, but including the matroid in some sense, generalizing the matroid in some sense. So definition is very easy. So anti-symmetric matroid is just a vector in our projective space. I mean, you can understand this as just the set of the transversal or almost transversal satisfying the following restricted Grassmann-Plicker relation over the Krasner hyperfield. Yeah, and yeah, this is our. I didn't write the set theory. I didn't give you set theoretical definition of the antisymmetric matroid, but you can easily extract those kind of things from here. And the antisymmetric matroid coefficient is nothing but just restricted Grassmann-Plicker relation over our track F. So I will give you some properties of this antisymmetric matroid. The first one is this generalized matroid. And the second one is also not only the basis exchange axiom, it has some circuit axiom also. And the other thing is I already introduced about this parameterization phi, but it can be extended for arbitrary track F. So what it means is if F is our Krasner hyperfield, then this is nothing but a circuit, the cryptomorphism between the basis exchange axiom and the circuit axiom. And yeah, you can extend this kind of things for any other field, any other track. And for the special kind of track, yeah, it gives some different things. So very special thing is when 1 is equal to -1 in the track, or you can easily consider this as an extension of the characteristic 2 field. Then in the characteristic 2 field, you know that every skew symmetric matrix is a symmetric matrix, but just by allowing certain non-zero element on each diagonal. And actually, we know that our orthogonal Grassmannian over this track is just subset of the symplectic Grassmannian. And it is also related to several other concepts, like Borla and Orter defined the symplectic Dressian using another quadratic relation parameterizing the symplectic Grassmannian. However, by just discarding certain amount of the information, we can get our antisymmetric matroid over the tropical hyperfield. And also this is related with the isotropical linear spaces defined by Felipe Lincoln. And another thing is, this gives some the definition of the oriented antisymmetric matroid. So I think there is no well-known concept about the type B or type C analog of the oriented matroid, but I give these things by just taking our F as a sign hyperfield, and this is also quite related with the oriented Gaussoid paper by this. And also another fascinating thing is this extend the Tuss theorem and the Mauro's theorem very well. So I will explain this a little bit later. So let's give you something more insight about the circuits of the antisymmetric matroid. So if you have some linear matroid, and then what you know is if you consider the all minimal supports of the non-zero vectors of this V realizing our matroid, linear matroid, then we already know that this is a co-circuit of our matroid. And we already defined our representable antisymmetric matroid using the maximal isotropic space by our parametrization. So if you take some support of this, then this is basis of the antisymmetric. If this is basis of the antisymmetric matroid M, then we can say that this is representable. And actually, what we can observe is the circuit of M, which can be defined very similar way to the original circuit of the matroid. So by just taking the minimal dependent set, in some sense, then it is nothing but a minimal support of non-zero vectors with some additional condition, which has at most one skew pair. So let's give some examples. So here W is here is identity matrix, and this is skew symmetric matrix. So this is the row space of our W is the row space of this matrix, which indexed by 1, 2, 1 star, and 2 star. And then because of our definition, we can easily get the antisymmetric matroid. And if you want to consider about each circuit, then you may consider about all supports of its rows. I mean, the space of its row spaces. And here, 1 and 1 star, 2 and 2 star can be obtained by just summation of the two rows and consider about each support. However, we say this is not a circuit of our antisymmetric matroid because it contains two skew pairs, 1 and 1 star, and 2 and 2 star. Yeah, so this is rough concept of our circuits. And actually, this is quite good because if you consider about any linear vector space, then we already know that if we consider the direct sum of itself with its orthogonal complement, then we already know that this is a maximal isotropic space. And the similar thing happens for the antisymmetric matroid. So if you consider our matroid, then if you collect our co-circuits together with the circuit with the star, then this is exactly the circuit of our antisymmetric matroid. And because of that, you can easily imagine that the circuit action for the antisymmetric matroid generalize the Mintis self-dualizing action for the matroid. And this is the reason why we can consider the antisymmetric matroid as a generalization of the matroid. Also, there is one funny relation with the Ribbon graph with the antisymmetric matroid. So yeah, so there is already very well-known theory about the relation between the Ribbon graphs and the delta matroid, and we also can extend this kind of a little bit more. And if you consider about the all, and so here Ribbon graph is nothing but a graph which is cellularly embedded on any closed surface. And if you consider the union of the cycle, which is minimally cutting the surface, then this forms an antisymmetric matroid. And here I lie a little bit, but we should consider the partial dual and the posterior dual as well. Okay. So okay, I promise you that I will explain why this generalize the Todd's theorem and the Mauro's theorem. So in Todd, he proved certain theorem about the matroid and the Grassmann-Plöcker relation in his paper. I don't know the title, but maybe this is paper which name is homotopy theorem for the matroid. Yeah, he implicitly proved this kind of result in terms of the chain group representation. So what he proved is if we have some point which satisfies all Plöcker relation, this is just nothing but our representation of the matroid. Or you can also consider this as a linear space. And then it is if and only if that it satisfies all three-term Plöcker relation, which looks like this. So this is the easiest non-trivial one. And if this is actually not enough to recover all Plöcker relation, but if we assume that our support of this forms the basis of our matroid, then you can, by induction, you can easily recover that all Plöcker relation. So and we can also observe the similar result for the antisymmetric matroid. So if you consider the point and satisfy, and if and only if it satisfies all restricted Grassmann-Plöcker relation, if and only if it satisfies it satisfies at most four-term restricted Grassmann-Plöcker relation, which are the most easiest ones. And also, if we assume that this is support forms the basis of the antisymmetric matroid, then you can inductively recover the all restricted Grassmann-Plöcker relation. And another thing is Mauro's homotopy theorem. So this is in terms of the basis, polytope, if you consider the one skeleton of the basis polytope, then if you just attaching the two cells along the all 3 cycles and 4 cycles, then this two complex is simply connected. So this is why we call this is a Mauro's homotopy theorem. But in the graphical sense, you can understand that if you consider the basis graph of the matroid, then all cycles are generated by relatively short cycle. What I mean short cycle means that the length M-3 or M-4. And we have some similar result for the antisymmetric matroid. So I will not define what is exactly the basis graph of the antisymmetric matroid is, but roughly speaking, it is also quite related with the basis polytope. And if we consider the just basis, it's one skeleton, and just certain rule, we just attaching some two cells along the cycles, then we can guarantee that these two complexes are simply connected. And this is very useful inductive tool for the prove our theorem for the Matroid with antisymmetric Matroid with coefficient. And also why I want to highlight more that is actually our theorem implies the original Mauro's theorem as well, because we already know that Matroid is the antisymmetric Matroid, and we can also easily find out some relation between their basis graph. So actually, this is my last slide except the thank you, but I want to say something more interesting thing lying on this kind of topic. So maybe you can, since we have now the oriented antisymmetric Matroid, so some people try to consider about some topological representation of the oriented antisymmetric Matroid. And something else is, still we do not have the flat axiom or something else. So I think it would be very interesting to find out some flat axiom or something else, or length axiom doesn't, I'm not sure that this makes sense or not, but it would be very fun. So yeah, this is end of my talk. So thank you.
Any questions for Donggyu?
So you're talking about SPN2N, or the Grassmannian SPN2N.
Yes.
And you also mentioned a couple times SON2N. So I see these like type C and type D. Is there a version of all this for type B?
So I didn't mention about the SON, this specialized orthogonal group, but something else. But so in the original, in the book of the Coxeter Matroid book, they, just consider B and C, type BC together. So I do not distinguish this type BC, so I don't know much about that. But yeah, if there are distinction between them, then that would be also interesting.
Yeah, so the results, the last few results, were like super similar to the original. How different is like the proof method? Is it roughly the same proof method, or is it completely different?
That's right. So roughly, I follow the very similar techniques in the previous one by the Baker and Bowler. But one hardest thing is this homotopy part. So the homotopy theorem for the Matroid was very well known, and also for the even symmetric Matroid we also already know. But to prove this part was one of the hardest part, and except that everything are quite trivial.
Any more questions for Donggyu? Okay, let's go to lunch then, and remember to be back here in an hour.